All right, we're recording. So, hi everybody. Yeah, so today I'll be talking about the number of solutions of a Thue equation. This is once again, this is the problem that my supervisor gave me to think about. He has made a major progress on this problem back in 1991, and I'm probably not going to mention it today. But what I'll be mentioning. I'll be talking about today is something a bit different. This was the paper that preceded the work of Cam Stewart. This was the work of Bambieri and Schmidt, and in fact, the technique that they use to approach this problem is nowadays pretty standard. So if you see any papers that appear after Stewart's publication, and including Stewart's publication too, they all basically use sort of the same approach on how to solve the Thue equation. So here's the agenda, and yeah, let's just start. So some background. What I'm interested in is in Thue equations. The Thue equations, but for the Thue equation, I define. Oh, that's very convenient. So I'll be defining a binary form f right here. Of degree d greater or equal than 3, and m is just an integer. I guess 0 is not an interesting case, but yeah, just some integer. In 1909, Thue showed that the equation f of xy equals m has only finitely many solutions, integers x and y. Do we remember what a binary form is? It's a homogeneous polynomial in two variables with integer coefficients. So this equation over here is called the Thue equation, and I guess I should probably write it out because we'll be using these numbers across the slides. So this this is an equation 1. So a solution xy to the Thue equation is called primitive if x and y are co-prime. In 1930s, Siegel conjectured that, in fact, the number of primitive solutions to the Thue equation should be bounded about by some constant which depends only on the degree and only on number m. Okay? And note that it's important to emphasize that we're interested in primitive solutions. Why are we interested in primitive solutions? Because there are examples if we consider in general solutions that are not primitive, then the number of solutions can actually be unbound. It grows with m. In particular, right? So something like that. So the conjecture was resolved by Evertson in 1983. He showed that we can take the constant of this form. Please remember number t over here, which denotes the number of prime factors of m. So throughout this talk, I'll be using t. T always denotes the number of prime factors of m. And in 1987, Bambieri and Schmidt showed that, in fact, we can take a constant c of this form. So, in fact, we just moved d, appearing the exponent, down, right? So now it's d to the power of t, and the constant c0 is absolute. So that's what I'm gonna try to do in this talk. I'm gonna try to explain to you the proof that Bambieri and Schmidt did. Okay, motivation, once again, nowadays this is a standard approach to this particular problem. Since 1987, there have been quite a few improvements, and if I understand correctly, that I'll be also speaking next week too, right? So I was hoping that next week I'll be talking about that stuff as well, but next time I'll be speaking about the improvements made on this particular problem. Okay. And here's the paper, so if you're interested, you can always look there for details on the proof, because I'll try to go through the whole proof, but of course I want to swipe many things onto the rug, okay? The proof strategy is, let me outline the proof strategy so you can actually be made pretty clear. What we're going to do, first we're going to not look at the original Thue equation, but instead I'm going to be looking at the equation of the form, the absolute value of xy equals to m. So now, of course, it makes sense to pick m to be a positive integer. And I'll be counting the solutions x, y, and minus x minus y as the same thing, right? Quite easy to verify that if one of them gives a solution to one prime, then so does the other one. Also, what we're going to be doing is we're going to start with this equation. The absolute value of f of xy equals to 1. To approach the problem of solving this Thue equation, which basically asks whether or not the binary form f represents a unity, what we're gonna do is we're gonna divide. We're gonna consider we're gonna divide our solutions that we're trying to bound into two different kinds. There's small solutions and there are large solutions. So let's see what those are. So intuitively, the large solutions are those which have, well, y being really large, okay? And of course, probably that would influence the value of x in some way too. So if I'm going to write my f as the product of linear forms of the form x minus alpha iy, so we have where alphas are just the root of this polynomial f of x1.
Are you assuming your f is monic?
Oh, right, you're absolutely correct. I need to put a constant over here, right? The leading constant. But, and I'll be pointing this out later. You're right. I can assume that it's monic. I can assume by considering the natural action of a L2Z on the set of binary forms, I can actually transform my function so that 1, 0 is the solution, and therefore the leading coefficient will be 1. Okay, but you are absolutely correct. In this case, there should be a constant, like the leading coefficient should be sticking around here. So as y approaches infinity, we note that well, I mean, in particular, this quantity becomes small, right? I mean, this is just approaching some constant, and for some roots, suppose that alpha 1, this will become smaller and smaller and smaller, and so eventually this quantity should be small too, right? But what does that mean? If from the perspective of Diophantine analysis, this means that x over y is an exceptionally good rational approximation to alpha 1. And if, for those of you who know Roth's theorem, which tells us that the Roth theorem essentially tells us that these kind of fractions that approximate alpha 1 in such a good the algebraic numbers in such a good way, they're very rare. Okay. And this is what we're going to use. Okay, there are quantitative versions of Roth's theorem, and this is exactly what we're going to apply to estimate the number of large solutions. So we use Diophantine approximation techniques here. Now, there's still a problem to deal with the small solutions, and this is how we're going to approach it. There is a natural action of a cell to z on the collection of binary forms, and in order to estimate the number of solutions, what we're going to do is we're going to find a better binary form for each solution. Okay, what does it mean? Well, I mean, technically, if I'm going to what I'm going to do is I'm going to produce an equivalent binary form which has exactly the same number of solutions. Okay, and so the counting property of counting solutions remains exactly the same, but the Diophantine approximation properties change drastically, of course, right? So something that wasn't a very good approximation something that was, for example, a very good approximation to one form may not be a very good approximation for another form. So that's sort of the idea that we'll be using here. And finally, once we deal with the small solutions, we will use Mahler's argument from 1960s, if I recall correctly, to reduce the original equation which involves m, so the absolute value of f of x, y equals to m. We're going to reduce it to a bunch of equations of the form fi of x, the absolute value of f I x y equals to 1, right? And it turns out that the number of these equations is going to be at most d to the t. Right, where t is the number of prime factors of m, and of course we will already know the upper bound on this particular equation. Therefore, thus the result. Right? Okay. Well, let's proceed. So we're gonna start by looking at the large solutions. How do we find out the upper bound on the number of large solutions? Before that, several results. So we know, here's the definition of a height. So we say that an integer point, xy, with co-prime components has, so a height of this point is defined as the max of the absolute values of the numerator and the denominator. Okay, right? And we have this lemma, which we're gonna utilize by Lewis and Mahler, which tells that if the distance between, so if we have our rational approximation x over y, and we're gonna compute the distance from x over y to all of the roots, and we pick the smallest one. So this is how we say that the rational approximation, this fraction x over y, is associated to one of the roots. So it's closer to one of the roots than to all of the others. Then it turns out that this inequality holds, and m of f over here is the Mahler measure. Okay, so in fact we see that in particular it's. We see that it's, what is it, it's inverse proportional to the height of the, to the height of our point. Okay? So this is a very important inequality that we'll be using. So here's what we're going to do. For some y0 that I'm going to specify, right? Because I'm saying that I'm dealing with large solutions, but how large can they be, right? We need to pick up sort of a lower bound, starting from which we say, okay, so if our y passes this y0, then we consider the solution to be large. So fix some y0, then you consider all your solutions, and of course we can just restrict our attention to the case where y is positive, right? Because xy minus x minus y we're counting them as the same, and we're going to order all of these solutions one after the other in an increasing order of y's. That's what we're going to do. So then what we're going to do is we're also going to restrict our attention only to those solutions that are associated to a particular root. So I'm fixing a particular root, say alpha 1, and I'm considering all the solutions that are associated to this specific root alpha 1, right? So all of these numbers over here, so all these result in a fraction x1 over y1, which is closer to the root alpha 1 than to anything else, right? Than to any other root. Okay? So now that we have this ordered, we also note that we have this ordering on the heights over here, and you can use we can obtain from here, if we put c equals to this, and this c of course comes from Lewis and Mahler identity. We see that this inequality holds. How did I get it? Well, first of all, these two rational approximations, right? I mean, these are rational numbers, and they're different, right? They're reduced, so therefore this must be the case, right? So the lower bound is clear, right? As for the upper bound, how would we obtain the upper bound? Well, I'm using the triangle inequality here, right? So I can just, starting from here, I'm going to plug in alpha 1, subtract alpha 1, and add alpha 1. Make it less than or equal to alpha 1 minus xn over 1n plus alpha 1 minus xn plus 1 over yn plus 1. And then I apply the Lewis and Mahler identity, okay? And that's how I get these two inequalities here. Well, why is it good? Well, that's because we can actually now apply, we can actually conclude that this thing holds. Look what we just did here. We started with the height on the n plus first point, and now we showed that this height should be greater or equal than the height of a previous point raised to the power of d. Okay? So now we can actually apply an easy induction, and in the end we yield what is called the strong gap principle. So the strong gap principle tells us that the height of xn, yn exceeds this value. And note that it's actually, why is it a strong gap principle? What it shows you is that the solutions should really, really repel each other, right? Like note that what you have in here, you have, not only you have the power d of minus 1 here, you're raising d minus 1 to the power of n, right? So if such large solutions exist, they just exponentially far apart. That's sort of the idea. The gap between them grows not even exponential, it's even more, right? It's much faster than exponential, right? This is what it tells us. However, it still doesn't prevent the infinity of such solutions exist, right? It just shows that any two consecutive solutions should be really far apart. This is what it. So what do I do to obtain an upper bound on the largest solution? That's the question. And this is what is called the Thue-Siegel principle. What Siegel found out is the following. We introduced the definition of a very good approximation. So far, I was sort of how would I say? I didn't formalize what a very good approximation is. Okay, in this case, this is the formal definition. Like, I mean, we don't have to go through all of that. Okay.
Here, your t can't be the number of prime factors of something.
Oh, I'm sorry. Yes, you're absolutely correct. Yes, this t, of course. Yeah, you're absolutely right. This t is, of course, not the number of prime factors. Yeah. So you pick these coefficients t and tau over here, and in the end, you define your really good approximation. So you pick all your parameters according to this rule over here, and in the end, you say that okay, I'm calling x over y a very good approximation, and this thing holds. Okay, and now here's the Thue-Siegel principle. It tells us that if there are two very good approximations, then the following inequality holds. Okay, and in fact, this inequality is precisely the key of obtaining the upper bound. It tells us that that any two solutions, they can be, well, I mean, they are far apart in the sense of a strong gap principle, but they also cannot be really like super far apart from each other. And that's what this thing tells us. And in the end, now you can combine these two principles, right, in order to obtain your upper bound. So by picking the correct value of y0, you can, and setting up, which basically, if you pick this particular y0, this inequality would hold, right? You can apply both principles and get your result. So now, once again, we can apply the Thue-Siegel principle. We obtain the lower bound for log of h of xn yn, which appears over here, right? We can obtain the lower bound from the strong gap principle, and we get this kind of inequality. So from here, you can actually, here's your n, take logarithms, and in the end, work it out. You find out that your number n is bounded from above by some constant, which depends on d. So the number of primitive solutions to the Thue equation, where we're asking for the number of representations of unity, for y greater or equal to this y0 is this. And eventually, if you pick your d to be sufficiently large, you can actually show that it's less than or equal than 3d. Okay? Well, I mean, I guess that's clear from here, right? I mean, if your d is large enough, eventually it's going to be more. You can bound this thing by 1. That's sort of the idea, right? Okay, so are we good with the understanding how did we handle the large solutions? Okay, so this is how we deal with the large solutions. The only thing that is left for us is to understand how to bound the number of solutions that have y less than or equal to y0. Okay, this is a bit more tricky. Well, actually, I would say that algebraically, it's actually easier because it's only doing some kind of estimates, okay? But you have to be very careful with these estimates. So now let me introduce to you the natural action that I mentioned before, the action of the action of I guess in general integer matrices, 2x2 integer matrices on your well, no, I guess action is the term that applies to groups, right? And
yeah, so it's like a GL2C action on the space of degree D binary form.
Yeah, exactly. But in any case, so if you have let's put it this way, if you have an integer valued matrix, right, and you can act by this, you can apply this matrix to your form in the following way, right? So if you have your matrix A, B, C, D are integers, you can produce a new form by simply substituting xy with ax plus by and cx plus dy, okay? This is just in a straightforward identity that follows from that kind of a substitution, okay? It's not that hard to verify. And if we restrict our attention to SL2Z, then of course our matrix is invertible, right? So what does it mean? It means that solving the Thue equation for counting the number of solutions for f of xy or fa of xy when a is in SL2Z is the same thing, Okay, this number of solutions is gonna stay exactly the same, and so this is how we introduced it in the notion of equivalence of forms. Okay, so the forms fa and minus fa are equivalent to original form f, and what we're gonna do is we're gonna assume that the molar measure of our form f is the smallest among all forms that are equivalent to f. Okay, so we're gonna pick f of the smallest molar measure. Another thing that we can do, and that's exactly what Stanley pointed out before, is we can actually also assume that our function f has the leading coefficient 1. How can I do that? Well, I suppose that there is a solution to my equation. Then I can find a matrix in SL2Z such that if I act by the inverse of A onto my solution, I get 1, 0. Okay, so this is a system of two linear equations. You can easily solve it. In the end, you see that there exists an A such that if I act by A on my form f, I am getting a new form which has 1, 0 as a solution. Okay, so now I can also assume that my form f has a solution 1, 0. And I guess what I also forgot to mention is that over here this is also important. So I guess what I should be mentioning here is that I'm picking the smallest molar measure. I'm picking the smallest molar measure among all forms which has the leading coefficient 1. So that's also important. Okay? Yes?
Question. So how do we know that we can make or choose the smallest molar measure? Like this isn't.
Oh, why is there a min?
Minimizer, yeah.
Why is this a min and not an inf? That's a good question. I would say that, huh. Okay, how about, okay, so if I would, I don't know from the top of my head, but I think that in this case you can do a sort of a infinite descent of Dirichlet. But I know that m of f might not be an integer, but what I'm saying is that, like, I mean, there's countably many possibilities for m of f. That's sort of the idea. So I guess you can eventually, you can do that and eventually reach the minimum. If that would be my guess of how to do that, but yeah, that's a very good question. Yeah, I'll think about that. Yeah, but the minimum is achieved, okay? Are we good with these? With this setup, right? So, point to take from here, we have this. We have the leading coefficient 1, and we have the molar measure being the smallest among all the equivalent forms with leading coefficient 1. Okay, moving. The next thing. So I'm gonna denote by ND the maximum number of solutions to my equation over there over all possible forms of degree D. That's what I'm saying. Now, let P be a prime, and I introduce you two matrices, A0 and AJ. Well, actually, it's not two matrices, it's P plus 1 matrices. What am I doing in here is I'm subdividing my Z2, all the integer points, two-dimensional space. I'm going to subdivide them into different groups. These groups can intersect, okay? Another way of thinking about it is I'm basically taking my points, all of the possible points on the Cartesian plane, right, the integer points, and then I'm subdividing them into p plus 1 different lattices. Okay, so I have these p plus 1 different lattices. Maybe sometimes they intersect on the points which have multiplicity p, right, where x and y are divisible by p. That's what I mean. But eventually, you see that you can actually write down Z2 in this form. Why am I doing this? It turns out, well, I mean, obviously, if I'm going to apply this form now to my original form f, this is going to increase the discriminant. Why is this going to increase the discriminant? Because of this thing. So if the determinant of A over here is p, you are increasing your discriminant by p to the power of d times d minus 1. It turns out that if your discriminant is large, this helps a lot. Okay? In fact, if I understand correctly, in one of the once again, Stanley mentioned the conjecture, right, where we think that the upper bound on the number of primitive solutions should not depend on even on m. And it's an open problem. We don't know. It might depend only on D. And in fact, this solution, this is the case, so the upper bound doesn't depend on D, whenever your discriminant is large enough with respect to M. Okay? So that's the problem. So, but the main point to take is that when discriminant is large, with respect to M, we can actually obtain an upper bound which is independent of M. So that's what we're going to do here. What we're going to do is we subdivided our Z2 into P plus 1 different lattices, and now we produce P plus 1 new forms by acting with these matrices, each of these matrices on F. Okay? So now the number of my solutions on the number of solutions to the Thue equation representing the unity is bounded about by this number, which is where N0, N1, and NP are just the numbers that are basically the number of solutions to each of those f of aj. That's what they are. But in fact, I can generalize it a bit more, and I can say that, okay, so I'm going to merge all of these things together. And how I'm going to merge it, I'm going to introduce a new constant NDP, ND of P, which basically asks for it is the largest number of solutions of the equations of this form where the discriminant satisfies this, when the discriminant is larger than P to the power of D times D minus 1. So if this is the, so I'm asking, so this is, so once again, ND of P is the maximal number of solutions over all forms with the discriminant at least this big. Good? Moving on. So now we're actually going to go into the actual estimates, what they do. So suppose we have two solutions, x and x0. I'm going to write them down as vectors. So now I'm going to write down the linear forms, Li of x, x minus alpha iy, and this d over there, it's not that important. It just appears in the next lemma. The lemma tells us the following, that this quantity over here, if this quantity over here is connected to the two roots for some other form g, which is equivalent to original form f. That's what it tells you, okay? So if you fix, so suppose x naught is fixed, you pick some other solution x. Now, from these two solutions, x naught and x, you can produce a new form which is equivalent to the original form. This is the form, and beta i's are just the roots of this new form. So they are somehow connected to alpha i's. Okay. So we hope that this new form will somehow give us a bit more information about that. This new form will give us will be more convenient to work with. That's the idea. Okay. Also, I wanted to point out that this form g hat is also equivalent to the original form f. Right? So if you have some form g equivalent to f, well, obviously if you shift the roots by some integer m, this is just acting by a matrix of the form 1m01. That's what it does. So this kind of form g hat is also equivalent to f. All right? Moving on. Now, we do know one of our solutions, right? Remember, we do have a solution 1, 0. And that's so we're going to fix our x0 now, and then if we apply the lemma, we have this simple looking equation. Okay, so once again, these beta j's and beta i's really depend on your choice of x. So depending on my small solution, I'm picking a different form. Okay. For every x satisfying the Thue equation, I choose a j such that my linear form, the value of, oh, there should be an absolute value over here, so I apologize for that. Of course, there should be an absolute value, but if you write down your f of x as simply as a product, right? Because that's what it is, f of x factors as a product of linear forms, then at least one of the linear forms has to be greater or equal than 1, right? I mean, the value at x. Right? So that's what I'm going to pick. I'm going to pick my j with respect to x. But then what I can deduce is this kind of inequality. Where does it come from? Well, first you show that this this fraction over here, 1 over absolute value of Li of x, is greater or equal than bj minus bi. How do you show that? Just use this. So first you show that it's bj minus bi. Then, because this thing is greater or equal than 1, the absolute value of it, therefore, if you put a bar on top, so you complex conjugate it, it's still going to be true. And so you can, and you can show that you can replace, instead of bj, you can put bj bar over here. So it's a conjugate over here. Now you combine these two, and you deduce the information on the real part, okay? And that's how you obtain this inequality. So now what I'm going to do is I'm going to pick an integer with respect to my x, okay, and make my m as close to the real part of root beta j as possible, okay? So I picked my m, and then from here I can show that this inequality holds for every single I choose, okay? Good? Moving on. Now, here's what we're going to do next. The solutions that bring us most trouble are those solutions where the linear form, one of the linear forms are unusually small. And that's the solutions that we would like to count in particular, okay? So, here, let me introduce a definition. I'm going to put all these solutions, of small solutions with small linear form. I mean, I guess it's not unusual because they bring most of the small solutions come from there, okay? So I'm going to put them in a single set and call it xi. So I'm going to call a set xi to contain all the solutions up to y0 that we already specified, such that the linear form Li, the ith linear form in particular, does not exceed 1 over 2y. Okay? Now I would like to estimate how big this set is. We're going to do 3 lemmas, and in the end I'll be able to make some conclusions here. Well, first of all, you can show that in fact within this particular set xi, the following inequality holds. So you can actually say how big is your next solution with respect to the previous one. Okay? This is actually not that difficult. You basically just use the estimates. Okay? And of course, over here, your beta I and m, they are connected. And they're connected to x in particular, right? So this is still x dependent. The next thing what we're going to do is we're going to look at other solutions. Okay, what if the linear forms that we're looking at is actually greater than 1 over 2y? And it turns out that we have this nice inequality over here, the absolute value of m minus beta I less than or equal to 7 over 2. And the proof of this factor is rather simple, right? Just take m minus absolute value of m minus beta I, and I guess that's how simple it is. This actually, the proof of lemma 3 is not much difficult. It's just a bit more lines, but in the end, it's the same kind of thing. Okay, so now that this case deals with the solutions which have one of the linear forms really small. This case deals with all the other solutions. Moving on. Now, for each xi, what I'm going to do is I'm going to throw away I'm going to order all the solutions inside of xi, right? And I'm going to throw away the one which has the largest y. Remember that we assume so far that y's are positive, right? So throw away the one that is largest. So we basically, if we are removing something, we're removing at most d possible, at most d roots. Now let x be the set of solutions with these maximal numbers removed from xi. Okay? And now I'm ready to actually prove the lemma 5. Okay? So what it tells us the following. If you have your discriminant sufficiently large, so in our case it should satisfy this particular inequality. So if you pick a large discriminant, then for epsilon greater than 0 and sufficiently large d, your set x has cardinality at most this. So we obtained an upper bound on the number of small solutions. How can I prove that? The proof is not that difficult. Well, first of all, you apply lemma 4. And what the lemma 4 tells you is this. The lemma 4 allowed you to deduce the information on two subsequent solutions, like the ratio of the denominators in your solution, right? Now you're just going to apply it n times over here. Actually, it's n minus 1 times. So what are you getting here? So you're going to compute the products of these things, n minus 1 times. So what are you getting on the right? You have y2 over y1 multiplied by y3 over y2, so y2 cancel each other. y4 multiplied by y4 over y3, y3 and y3 cancel each other. Okay, and eventually you obtain y0, right? Because all of your y's, all that you're left with is yn over y1. You can assume y1 is 1, right? So bounded from above by yn, but yn is less than or equal to y0. So this is your right-hand side. And on the left-hand side, you have this nice expression, okay? And by the way, look at this thing over here. This looks suspiciously like the element in the product for a molar measure, right? Because remember I mentioned to you that this thing looks like a root of some form which is equivalent to the original one. And that's the idea here. I'm going to transform, by doing this kind of product, by doing this kind of products, I'm going to obtain a molar measure eventually, okay? Oh, and by the way, I forgot to mention one important thing. For now, I'm fixing my xi, okay? So now I is fixed, okay? And within this I, for each x, of course, these beta i's and m's, they change, okay? So they change. But eventually, I get this, and then I'm going to multiply all of these expressions together over my i's. That's the idea here. Okay? By lemma 5, if I'm going to consider the same kind of expression, right? And we're going to see, oh, I believe that over here it should be m of x. It should be m of x over there, right? So over here, I forgot, minus m of x. But if you're gonna do the same kind of operation, you see that the absolute value of bi minus m, there it is bounded above by 7/2, which means that now if I'm gonna multiply, this thing doesn't exceed 7/2, so multiplying 2 over 7 by 7/2 gives me a bound of 1. So now I can multiply this thing, which varies over all x in xi, by all the x's outside of xi, right? So I'm getting essentially all of them. So here's what I'm getting. I'm getting that this expression here is less than or equal to y0. Now, once again, this was considered over all i's. Let's just compute the product over all i's that I got. What am I getting? Well, so here I remind you that we have this equivalent form, g hat. And also, I remind you that our f has the smallest possible molar measure, which means that the molar measure of g, of hat g, clearly cannot be smaller than the molar measure of f. Well, this helps us a lot, because now if I'm going to multiply all the expressions of this form, d times, right, for various I, I'm going to get precisely the molar measure of g hat, and this is greater or equal than the molar measure of f. And of course, now that I'm going to multiply these two together, right, this one and this one together, right, and then I'm going to multiply over all i's. Guess what I'm getting? I'll be getting on the left-hand side, it's going to be precisely the cardinality of x right here at the top. And that's exactly what I need. I need the cardinality to appear there at some point in order to make the state, to compute the upper bound. Of course, taking the logarithms, counting the fact that our discriminant is of this form for some prime p, and we eventually get this upper bound. Okay? So it's just very clever way to play with the estimates, and noting that at some point when multiplying over all i's, we're actually getting the molar measure of this form over here. So it's a clever approach. So this is how from here you can deduce the upper bound on the number of small solutions. Okay? And now how do we merge these results together? Well, let me let's just put them all in one. First of all, we know the number of small solutions we have is this, but remember that I excluded d largest values, right? These d largest values of xi. So at least I have to add one d over here. So there it is. It appears right there. So I added my d, and as we mentioned, for sufficiently large d, there are less than or equal to than 3d very good approximations. So I'm going to add that too. So here's our upper bound is this. And now, counting this fact and using the upper bound on the cardinality of x, we come to this conclusion that the upper bound on the nd is at most the nd doesn't exceed this value, and if you pick p equals 19, then you can actually make this kind of conclusion that nd doesn't exceed 215d, right? So this is your C0, right? Oh, then I guess my C0 is not absolute because it depends on d, right? So I guess I should write it down as d to the power of 1 plus t, right? Because my C0 is 215. That's what I'm saying. So there's a typo there. But you see what we did here. This is the approach for the proof. Any questions? Suggestions? Complaints? All right.
What's the epsilon?
The epsilon. Oh, it's just some positive number. I guess I should mention it at some point.
Yeah, like it counts
Yeah.
if you pick epsilon equal to 1 over 12. So.
Yeah. So I guess when they were stating this lemma, this particular result, they said let's pick an epsilon, and I just forgot to mention that you should just pick any epsilon greater than 0. Yeah. Are we good? All right. Finally, right now we need to move from the number of solutions to absolute value of f of xy equals 1 to absolute value of f of xy equals to m, where m is some arbitrary positive integer. This is how we do it. The general Thue equation, we can do it by means of the p-adic analysis. We're going to simply reduce our original equation absolute value of f of xy equals m to many equations of the form absolute value of f of xy equals to 1. So this is just a lemma. It's actually not that difficult, but what it tells you is that if you have a form f, okay, and you have a bunch of p-adic roots, then you can produce, and this is not a form, I guess it's a polynomial in ZP. Then you can actually produce then all the roots, right? Like, I mean, they're sort of disjoint from each other in the p-adic sense, right? So if you so eventually, with fixed number mu over here, you can find numbers a sigma and b sigma, multiply p to the negative mu by your function f over here, and in the end get a new kind of polynomial which is sort of associated, which still has a p-adic coefficients in the p-adic integers, okay, which is sort of associated to this particular, I guess, this particular p-adic root that you're talking about. Does that make sense? Okay. So once again, I can take my original. I can take my polynomial. I have a p-adic root, okay, and I can say I want an approximation of this root to be up to p to the mu, right? Then I can find the numbers a sigma and b sigma, so that this resulting polynomial, I mean, it still has content 1 when f has content. Well, I mean, content prime to p. That's what it says. Then this guy will also have content prime to p. And you're getting a new polynomial with all the numbers appearing in ZP. How does that help us? Well, here's the thing. Write your m as the product of powers of primes. Let your f of x, your polynomial that appears in the lemma before, be capital F of x1. Pick your p to be p1, and pick your mu to be b1. By the lemma, there exists a sigma and b sigma. Oh, there should be f over here, of course. Apologies. Such that this polynomial, attention, it has integer coefficients. And why is that? that guy originally had integer coefficients. Therefore, I can pick my A sigma and B sigma to have integer coefficients too. So in the end, I'm producing a new polynomial with integer coefficients. And now I am going to apply. So here's by the way, here's the choice of B sigma and A sigma that I choose. And L sigma, of course, over here, of course, it varies. It is actually, I believe it's actually equal to B1 for when P1 does not divide the discriminant. But if P1 does divide the discriminant, L sigma can be different. Okay? So these, what are called irregular primes, they always bring us some trouble here. But in the end, the main point is that these things are integers. In the end, you're getting a new polynomial with integer coefficients. Now, apply this logic to your binary form, F sigma. Do this kind of substitution. And guess what? You're getting a binary form with integer coefficients again and content prime to P. Okay? So this bilemma 6b, this thing has integer coefficients. And now we observe that whenever our y is comprimed to P1, I can actually write down any solution x over y, because that's precisely what it tells you, in this form, A sigma z plus B sigma for some z. But then, of course, I can just rearrange it. And observe that my z should be a fraction. Okay? Which means that I just produced a solution, a new solution for this kind of equation. So the x star and y star are a solution to this kind of equation. And you see what I did here? We just removed the factor of P1 to the power of B1 on the right. So this is how the reduction appears. And of course, if my y is divisible by P1, I can perform the same construction with x, right? Replaced because x and y are coprime, okay? So I can just do the same kind of construction for the polynomial f, capital F of 1x. And now we see that the total number of these forms, the total number of binary forms that we produced in this way is at most d. Why is it at most d? Because we can have at most d solutions in the p-adic numbers, right? In the p-adic integers. At most d, so we obtain d such equations by removing one single prime factor. Now guess what's going to happen next? Well, we're gonna actually reduce it for every single prime. So in the end, we obtain d to the power of t, where t is the number of prime factors of m. So there you go. And yeah, thank you very much for listening. And let me just, I guess, a quick, brief, last note that I want to make is what was Stewart's achievement in this field? Well, the thing is that he was able to remove, so that if you actually write down your equation, that if you write down your upper bound as what is it, C0 d raised to the power of omega m. That's what omega is, the prime counting function, right? The number of prime divisors of m. What he did is he was able to show that in fact you can take this thing to be omega of g, where g
That should be 1 plus.
1 plus, yeah, you're right. And over here it should be 1 plus 2, by the way, right? Yeah. Omega of g, where g is a large prime divisor of m. So you can actually, instead of m, you can consider a large prime divisor. And of course, a positive proportion of numbers have very large prime divisors. Okay.
100%.
100% of.
Epsilon's 100%.
Is g the prime divisor? Omega of g is just.
Yeah, exactly.
That's the whole point. That's the whole point.
Yeah.
So for when with this thing, we can actually show that for what is it? So it looks like for 100%, like of numbers, you can just pick your upper bound to be C0 times d squared. However, there's still some numbers that bring us trouble, okay? And so it is still, and once again, I would like to mention that the conjecture here, and this is due to Erdős, Stewart, and Tiedemann, that in fact you can remove the dependency on m at all, okay? You can it should be just dependent on d. It looks like that. Yeah, all right. Questions?
Yeah, any questions?
Yeah, so when you show that the large solution is finite, like bounded by 3D or something, you already showed that all the solutions are finite, like the rest, like the small solution, just a better boundary on the number of solutions, right?
Repeat your question again?
So when you show large solutions finite, you pick out like all the y's greater than equal to y0 or something, right?
Uh-huh.
And then the solution to the Thue equations are automatically finite already, right? So
Yeah, because
we
when
have
you
like,
picture why not.
Yes, yes, but yes, of course, it is finite.
So then
It is finite, but the main
small solution is just the bound under.
yes, of course, the number of solutions is finite. You're absolutely right. But the main point in here, right, is that what is it? You need to find a quantitative argument, right? You need to count how many of them are there. You see, and that's why we actually do need to know. Okay, how large can a solution be? I mean, yes, it is finite. We know that it's finite, but how large can your h of x and y and b? That's the key question.
Any other questions? Thoughts?
Thank you very much.
Okay, but I do have a couple of comments. So first, you cannot improve on in terms of order of magnitude, on the D and the 3D, right? Because you can find examples where f of x equals 1 has exactly D solutions. So the second comment, next comment, so the answer is SL2Z is a discrete group, so if you fix a form, you look at the orbits, they're discrete, so they can't have any accumulation points, so you can't have a converging sequence of Mahler measures. There has to be a minimal one. Yeah, I guess that's it.
All right, thank you very much. Yeah, all right.